So let's spend some time talking about how to draw Lewis structures. And again, hopefully you watched the lecture video and you went through the Lewis structures in your notes, but I think it's good to go through them again, make sure there's any questions outstanding that we kind of tackle those. And so the bottom line is we are still following the octet rule. And so I think the thing that's a little funny for folks who haven't seen this method before is what's called the octet number. And all this means is that metalloids and nonmetals, I'm going to use the word want, even though that's, not true. But to become stable, they want 8 valence electrons. They want to look like a noble gas. There is one exception, right? The exception that we're going to see often is hydrogen. Hydrogen wants to look like helium, and so its octet number is 2. And so we are going to make sure that we deal with hydrogen as special during this. But other than that, the idea is the other nonmetals and metalloids are going to try to gain enough electrons to get to 8. And we're going to utilize that fact to determine what our deficit is. So let's look at our first example. And I'm going to go just a little bit different approach. Again, we have our formula that we're going to rely on here. And so in this particular case, we have SOCl2, which means that we have a sulfur, an oxygen, and 2 chlorines in our formula. And so what we want to do is we want to calculate the number of valence electrons and the octet number. And so remember from the first page and from what we've been dealing with previous that group number is equal to valence electrons. So I go to the periodic table, I find sulfurs in group 6, oxygens in group 6, and chlorines in group 7. So I add that all up, and I end up with 26 valence electrons. Now, the issue is the octet rule, right? The octet number comes from the fact that all of these nonmetals would like to go from the number of valence electrons they have to 8, right? So sulfur would like to have 8, oxygen would like to have 8, both chlorines would like to have 8. And you can kind of see, right? Sulfur's missing 2, oxygen 2, each of the chlorines 1. And so the total number of electrons you would need to give those 4 atoms 8 electrons is 32. And so what this allows us to do is calculate what's called the bonding electrons. The number of electrons that are shared, those get counted twice. And so we can make up that deficit. So all we do is we take the octet number 32 minus our 26, and that's going to give us 6 bonding electrons. Now, those bonding electrons are going to show up as 3 bonds, right? 3 lines when we say bonds. Remember, each line represents 2 electrons. Now, once we have figured out our bonding electrons, our original 26 electrons minus those 6 bonding electrons means there's 20 other electrons that aren't involved in bonding. They're just going to be dots. They're owned electrons. And what we have to realize is that those 20 electrons are going to show up as 20 dots. However, they're going to show up as pairs of dots. So we are going to have 10 pairs of dots. So that's the math that we need to do. We're going to go through that same calculation every time. And again, we want to make sure that we realize that for us, we're following the octet rule. We're only dealing with stable molecules, so everything is going to have an even number of dots, but also those dots are going to show up as pairs. Now, you also need to figure out the central atom, what goes in the middle. And it's the least electronegative atom for the most part, right? It goes in the middle because it's going to share more willingly the things that are really electronegative, that are pulling electrons towards it. It's going to be the first thing listed most of the time. But once again, you have to make the caveat that it can't be hydrogen, right? Hydrogen cannot go in the middle. So let's start to put together our structure. So my S is going to go in the middle, and the first thing you want to do is pay attention to your formula. I also have to bond an oxygen and 2 chlorines to my sulfur, right? That's what the formula says. At that point, I need to check my bonds. To bond those 3 atoms of sulfur took 3 bonds. That's what I calculated, so I'm done with bonds. Now I have to add my pairs of dots. And so you're going to add your lone pairs so that an atom has a total of bonds and lone pairs of 4, right? Again, that's the octet. Every line is 2 electrons, every pair of dots is 2 electrons. Again, we're going to put the caveat on here, except hydrogen, which makes 1 bond and only 1 bond, right? It's got 1 electron, it's going to share that 1 electron. So the idea here is, when I get to my chlorine's got 1 bond, so it needs 3 lone pairs. And so I can put those 3 sets of dots on the 3 open sides. Same thing with this chlorine. It's got 1 bond, so it needs 3 lone pairs. The oxygen up here has 1 bond, so it needs 3 lone pairs. The sulfur has 3 bonds, so it needs 1 lone pair. And there we go. There's my Lewis structure for SOCl2. I've used up all 10 lone pairs. I've used 26 electrons. I've given everything an octet. There's a couple of other things that we want to make sure that we're able to handle. One is charge, right? We're going to be able to draw the structure of polyatomic ions. And so here we have NO2, so that's nitrogen and 2 oxygens, and then we have a negative charge. And so charge affects number of valence electrons. And so when you go to calculate valence electrons, again, you go to the group number. Nitrogen is in group 5, oxygen is in group 6, so that gives you 17. That's a good indication that you need to do something else. You should have an even number. Remember that if you have a negative charge, you have to add an electron to your total, right? You get a negative charge for the gaining of electrons. Electrons are negatively charged. So that's going to give us 18 valence electrons. The octet number is not affected by this, right? The nitrogen still would like 8. The oxygen would still like 8. The other oxygen would still like 8. We only have 3 atoms, right? The charge here is not an extra atom that wants 8. It's just an extra electron that has been gathered from somewhere else. And so my octet number here is 24. So I can take 24 minus 18. And once again, I have 6 bonding electrons. Divide that by 2. I get 3 bonds. 18 minus 6 gives me 12 non-bonding electrons, which means I'm going to need 6 lone pairs. My central atom is going to be my nitrogen. And one other thing to keep in mind is if you have an ion, you want to put the structure, put your Lewis structure in brackets, just to let everybody know. So when I start to draw this, I'm going to put my nitrogen in the middle. I'm going to bond my 2 oxygens to it based on the formula. And then based on the formula, I know that I have a -1 charge. If it was -2, I put -2, +1, whatever the charge is. That's the only thing I have to worry about in terms of the charge. Otherwise, it's been accounted for in the math. Now, as I do that, I've accounted for my formula, but I haven't accounted for all the bonds I need, right? I need 3 bonds. To bond those 2 oxygens to nitrogen only took 2 bonds. So I need to add a 3rd bond. And so I got to put it either here or here. Doesn't matter which one. No, it does not. Right? Either one is acceptable. So I will make this a double bond. And now I've accounted for my 3 bonds. Now all I got to do is add my 6 lone pairs. And I'm going to do it based on the number of bonds that each atom has. This oxygen has 2 bonds. so it needs 2 lone pairs. So I can pick any 2 of the 3 open sides. My nitrogen in the middle has 3 bonds, so it needs 1 lone pair. I'll put it on top. I could put it on the bottom. This oxygen has 1 bond, so it needs 3 lone pairs. And so the other 3 open sides will get 2 dots each. And so there is my 6 lone pairs taken care of. And that's my good Lewis structure for what's called a nitrite ion. All right, let's look at our last example, because here we go. Here's hydrogen. Alarm bells going off. Hydrogen affects the octet number. So, when we look at our formula, I have an H, I have a P, I have an O. In terms of valence electrons, no different, right? Hydrogen is in group 1, so it starts off with 1 electron. Nitrogen is in group 5, oxygen is in group 6. I've got 12 electrons to work with. But in terms of octet number, this is where hydrogen plays a role, right? Its octet number is 2. Now, my phosphorus still wants 8, my oxygen still wants 8, but what that does is it's going to give me an octet number of 18. And then that's it. That's the only effect on math. The rest of the math flows the same way as before. 18 minus 12. I have a 6 electron deficit, which means I'm going to need 3 bonds. 12 minus 6 means I'm going to have 6 non-bonding electrons, right? These 2 always add up to this one. And I'm going to have 3 lone pairs. Now, there's some other things to keep in mind. Since hydrogen makes 1 bond and only 1 bond. And so that means that hydrogen can't do a lot of things. Hydrogen can't be in the middle. It can't form a double bond. And it can't have lone pairs. So, let's start to put together our structure, right? A phosphorus is going to go to the middle. It's the first thing listed, not hydrogen. Then my formula says that I need an H and an O bonded to my phosphorus. So there's my formula. But I need a 3rd bond. And so can I put it here? Absolutely not. It has to go between the phosphorus and the oxygen. So there we go. That's my 3 bonds. Now, when I go to put in my lone pairs, again, I need to put in 3 lone pairs. No lone pairs on hydrogen, ever. And so my phosphorus has 3 bonds. It gets 1 of my lone pairs. And then my oxygen with 2 bonds is going to get my other 2 lone pairs. And so again, any of the open sides. And so there is my Lewis structure for HPO. Now the other thing I'd like you to be able to do is interpret a Lewis structure, and you could do the same method that we did at the top. Do the math. You could add up all the carbons, hydrogen, and oxygen in this structure and figure out how many valence electrons they have. But I would rather you work backwards. So again, number of bonds is simply the number of lines. And so if we go in here, right, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This one's 11, 12, 13, 14, 15, 16, 17, 18. There are 18 bonds in this molecule. Again, double bonds count twice. In terms of lone pairs, right, there's just 1, 2. Right, this is pairs of dots. To get to non-bonding electrons, you can multiply by 2. Right, this is the total number of dots, which in this case is 4. to get to the number of bonding electrons. Again, 18 lines means you have 36 bonding electrons, and so the total electrons is just just add these up, right? 36 plus 4 means I've got 40 total valence electrons in that molecule. And so I would challenge you to do the math now and see if you come up with those same numbers. You will. All right, so this is the biggest piece of today's packet. Remember, after today's packet, you'll be able to do homework 5. It's one of the few places I'm going to have you draw Lewis structures on paper, so make sure that you feel comfortable. Thank you as always for your time.